Hello, today I'll be presenting enClosure, which is a system for group communication via encounter closures. This is joint work I did with Roberta and Peter at MPI, Matt and Bobby at UMD, and Stefan at MSR. We focus this work on spontaneous and contextual communication, namely communication that requires no explicit exchange of contact details by the participants and corresponds to a particular time and place. Spontaneous and contextual communication links can form both among devices carried by co-located people, for example, two people happen to be at the same concert, and also among people on IoT devices, for example, an information beacon placed at a bus stop. This new type of situational communication among strangers has several requirements. It needs to be persistent so that people can message both during and after they have been co-located. And it should be privacy preserving, so users do not need to disclose their identity, their communication, or their whereabouts to any third parties, and they can't be tracked. It should also be secure so that users can authenticate their communication partners as those that they met at a specified time and place, and messages should be confidential and their content should be preserved. These requirements can be met by communication over secure encounters. In short, a secure encounter consists of a unique encounter ID and a shared secret between the two participants that is formed via a Diffie-Hellman key exchange. Each encounter ID is unrelated to a device's prior and future encounters, therefore ensuring that devices cannot be tracked. These encounters are stored in a per-device encounter history, and this information is sufficient for devices to securely communicate via an untrusted key value store in the cloud. Note that no device or user identities are used as communication endpoints. Instead, messages are addressed to the time and the place of an encounter. Encounters enable interesting new forms of communication. For example, a user can communicate with those she met at an event, for example, sharing photos or reviews with others at the same concert. Or perhaps she will want to message nearby resources for traffic information. Encounters also provide evidence of co-location. For example, a user can verify she attended a particular conference and therefore receive follow-up information. We are at the verge of seeing this type of communication deployed in the wild. Indeed, just 2 weeks ago, Apple announced a version of their Find My feature that uses encounters to find lost or stolen devices. And smaller companies such as Tile have been doing similar things for a while. However, today's encounter-based communication is limited to communication among devices that directly encountered each other or encountered the same access point. This artificially limits applications to those where devices were within radio range. For example, in this graph, the blue node can only reach devices encountered by itself or by the same access point. In this talk, we will show how enabling communication among devices connected by chains of encounters both overcomes these limitations and enables entirely new forms of group communication while retaining the same persistent privacy and security properties as before. We next introduce enClosure, which provides group encounter-based communication while still meeting the requirements listed earlier. enClosure acts on the encounter graph, in which nodes are devices labeled with a trajectory, and edges are encounters labeled with a time period. So in this bottom graph here, we can see how devices move across both time on the x-axis and space on the y-axis. And when they intersect, they form an encounter. enClosure enables communication among sets of devices connected by chains of encounters. Each set forms what we call an encounter closure. Closures enable communication among users who may never have met, who occupied the same area but visited at different times, who crossed each other's paths at different times, or who are connected by causal chains of encounters. To enable contextual communication, closures are constrained by space, time, and/or causality. These constraints specify the intended sets of receivers and thus act as the addressees of messages. Note that unlike existing forms of group communication, participants are not identified by their name, their address, or some type of topic, and they remain anonymous and untrackable. enClosure enables entirely new forms of multicast applications, some of which I've listed here. I'll explain next how applications can use these constraints to enable communication, focusing on two examples, a health risk warning and a call for information or witnesses. In a health risk warning application, messages are sent to an encounter closure constrained to those people who intersect an infected person during the time the person was ill. Furthermore, this application uses a causality constraint, which ensures that those receiving the message will pass it on to their future encounters along their paths within the contagious time frame. This approximates the epidemic spread of disease. Here, we show how users move across both time and space, and we can see that a user who encounters the infected person will have an encounter over which the message will be sent. The message is transitively passed on to devices subsequently encountered by the user. Our second application is a call for witnesses or information about an incident or a person of interest. For example, the police searching for a missing person would send a message along her trajectory since she was last seen in order to reach those who may have seen her. Here we can see how a user who encountered the missing person will receive the message. Furthermore, a user who had an encounter along the missing person's path at some later point in time, so to the right on the x-axis, will also receive the message. Note that this type of constraint also naturally enables applications such as lost and found. These are all examples of a class of applications that select communication partners based on the spatial, temporal, and causal relationships of their encounters. enClosure supports these applications spontaneously and securely without requiring users to disclose their identity, their whereabouts, or their communication. To compute these closures, we require knowledge of the encounter graph. But the encounter graph is sensitive because it includes devices' trajectories and encounters. So how can we protect these encounter histories while computing these constrained closures? Prototype, we rely on a trusted execution environment, which is the state of the art for secure cloud computing today. Only one possible approach. And we are also investing. Now we define our enClosure architecture. Together, these components perform encounter. The enClosure runtime on the device has multiple devices radio and forming encounters that are stored. To support enClosure messaging, applications talk to the enClosure library, which then communicates over encrypted channels to the forwarding cloud agent, which executes in a trusted execution environment. The forwarding agent has access to the device's encounter histories via periodic uploads by the enClosure library. And the agent is in charge of selecting those closures that satisfy a message's forwarding constraint. As noted before, an untrusted cloud key value store stores encrypted messages indexed by encounter ID, and devices can later query for their new messages corresponding to their encounter IDs. Before I discuss enClosure's security properties, I'll first present our threat model, which rules out sharing of encounter histories and radio advertisements among devices. Furthermore, we assume the cloud does not record client IP addresses, and we also trust the trusted execution environment and the cryptographic primitives that we use. Under these assumptions, we guarantee to a sender of a message that the message can only be decrypted by devices with at least one encounter that satisfies the message's constraint. Furthermore, we guarantee that the message will reach all the correct or non-malicious devices connected via encounter closures that satisfy the constraint. We also guarantee to a recipient of a message that the message has been sent by a device with at least one encounter satisfying the message's constraint. These guarantees are provided by what we call consistency checks, which enforce that both encounter endpoints must provide the same encounter trajectory in order for an encounter to be valid. Thus, a malicious device cannot forge an encounter with non-malicious or correct devices. We next evaluate our prototype of the enClosure design. So one natural question about encounter formation is how the enClosure runtime affects the battery life on commodity devices, and I'll address this first. Our prototype is a library for Android 8 running on Sony Xperia phones, where the key value store is hosted by Microsoft Embedded Social and is untrusted, and the forwarding agent runs in an SGX enclave. enClosure performs an asynchronous form of Diffie-Hellman key exchange, where the Bluetooth Low Energy controller broadcasts beacons and periodically scans for nearby devices' beacons. The CPU wakes up periodically to change the device's beacons, process received beacons, and form shared secrets. By measuring the battery life of a device while running enClosure in the background, we determined that the dominant factor affecting energy consumption is in fact simply the frequency of the CPU wake-ups. And we reduce these wake-ups by performing the Diffie-Hellman key exchange asynchronously. The number of encounters formed actually has little impact on the power consumption. With settings that wake up the CPU every 2 minutes, we show that a dedicated device running enClosure in the background and forming up to 256 encounters per hour will last over 10 days. In addition to measuring the energy cost of forming encounters, we also run a scalability test of Bluetooth Low Energy with 100 Raspberry Pis broadcasting unique advertisements in a confined space. And we note that not one advertisement is missed. These experiments thus indicate that Bluetooth Low Energy for encounter formation is practical in terms of energy consumption and can also scale to crowded situations. We also wanted to evaluate how messaging and enClosure applications would work in practice. While we evaluate several applications in our paper, I'll have time here to only present the health risk warning application. To demonstrate the utility and powerful capabilities of closures, we simulated applications on a synthesized encounter graph from the Snap Gowalla locations dataset. One such application is a health risk warning issued when a person contracts a contagious disease. We hypothesized that enClosure by providing a tool to anonymously identify potential. This application sends messages to people who encountered the sick person while the person is contagious, and people who receive this warning will send it. Here is a map showing the high-level results in Texas. You can see here that the message distribution reaches most of the contiguous United States and Western Europe. Our results clearly show that closures enable the application to rapidly reach the possibly affected population, even when they are spread across the globe. These graphs show time on the x-axis, and on the y-axis, the number of users in the left graph or the furthest distance reached in the right graph. The different lines on the graph show the users or the distance reached with varying chain lengths through the encounter graph. We can see that the reach of a message increases by orders of magnitude as we increase the chain length by even just a couple encounters. Therefore, with short chains in the encounter graph, we can address precisely the potentially affected population, regardless of their movements and without knowing their identities. In the absence of a system like enClosure, a warning would potentially have to be issued across the entire globe. enClosure is a new type of communication platform that can enable powerful new group communication applications. While we have presented the initial design and prototype, there are clearly still several interesting directions to pursue next. So first, we're actively working on strengthening our threat model. As mentioned before, we are investigating a cryptographically secure forwarding agent. We have also been thinking of ways to implement encounter histories as hash chains, which will enable additional consistency checks that will make it hard for a malicious device to fake a trajectory. One other property we can add to enClosure is the ability to handle various denial of service, network sniffing, and encounter graph mining attacks. In addition, as with most communication platforms, we have been thinking of ways to control unwanted communication. However, this is an interesting problem for enClosure because any would-be spammer must have been connected by a chain of encounters to their supposed victims and would have restricted scope. Finally, there are many interesting questions in terms of usability, how would applications be deployed, and what might their UI look like. In conclusion, I presented today enClosure, which provides a novel type of group communication that enables applications ranging from sharing photos of an event to collecting information about a missing person and even issuing health risk warnings. And it does so while fully preserving users' privacy. Furthermore, enClosure has a low barrier to entry. A user needs to do nothing more than run enClosure in the background to be able to communicate with others. You can find our paper and source code at the project page linked here, and I'm happy to take questions.